Thank you for inviting me here this afternoon. As the Professor's just said, there is a reasonable amount of information. I have got some handouts and we can arrange more. You can download them, I can post them out if you want to get them at the end of the session. There's also going to be references to industry guidance on how we do this and some sample calculations from our sister company's software output, which again we can make available to everybody after we've finished. Okay, you can all read, so I'll leave you to read that. But light gauge steel is comparable to timber frame in that it's a series of members at prescribed centres, typically 600mm. I'll go into that in a second, with floors spanning in between. We can do up to 30 stories, that's 30 stories in light gauge steel. When you see, which I haven't got a piece of with me, but when you see a piece of light gauge steel, they're normally C-sections, so it's lips, flange, web, flange, lip again, and it's typically 1.2 to 1.6mm thick. So 3 sheets of paper, and we're doing 30-storey buildings out of this stuff. You get a reaction from, say, older, I'm not young, engineers, people who've been doing this since I was a lad, etc. It's like, seriously? I'm not going in that building, let me stand up. But it really does. It's phenomenally strong. Oh, it is actually. We use generally quite high yield steel, 390, 450 yield steel rather than 275 for hot roll steel as well. It does have its problems, which we won't dwell on too much today, but things like acoustics. We make the building very, very strong, very, very stiff, which is perfect if you want to amplify sound or spread sound around the building. So we have to overcome that as part of it. One of the reasons we have this information is from an industry guidebook, but with some extra information for engineers. And it suggests acoustic performances. Now, if anybody knows anything about acoustics, you'll appreciate the first figure goes from 36 to 43 dB. The next one goes, the bottom one goes from 45 to 56. That's the difference between a whisper and somebody shouting at a football match. So the guidance is terrible from that sense, but there are people who can help with it, and we've got some indication here, etc., etc., etc. The other one to be aware of with the stiffness is the vibration of floors. Again, we have answers, we have solutions, and the floors do not vibrate if engineered properly. Although some of the issues people might raise when you mention you want to use light gauge steel. So to quickly cover the floor and answer it, we have 4 deflection checks. 2 are static, self-weights and imposed loads just like now. And we also have 2 dynamic checks, which are more, if it's not a wrong phrase, touchy-feely. A bit more, it's not pure maths, it's more how humans perceive the feel of the floor, which I know sounds a bit for engineers, but honestly, I joined the industry in 1999-2000. Just before I joined, somebody, I generally can't remember which company or engineer or anything else, but a manufacturer made some berths, some barracks for Marines. Supposed to be some of the toughest, hardest people around, aren't they? They felt seasick laid in bed in the light gauge steel buildings. How? What? Humans have their inner ear, which I'm sure you know, and it's like a little sack of liquid, and that detects movement. But we, as a race, are more susceptible to it when we lay down. So even people like that with a lot of experience of rough seas, etc., when they lay down, the floor was just vibrating at just the wrong frequency. As people are moving around, they felt seasick. Since then, we've introduced these 2 dynamic checks and we've got rid of that problem. The other thing is to increase the mass. We talk about lightweight floor, lightweight steel, light gauge steel, they're interchangeable. So what we can do is increase the mass. We could use concrete floors. Now you start using full concrete floors, 150mm slabs, etc., and you start losing the point of the lightweight steel. So there are other solutions, which again are on the other side of the sheet. One of which is a very, very shallow trapezoidal deck, metal deck. You know what composite metal decking is? Have you covered that? Yeah. One particular brand called Lewis deck. I'm not aware of any others, so I'm not promoting them. It's 15mm deep, and the overall slab is 55mm deep. So it's relatively lightweight. We're still looking at 1.2 kilonewtons, 1.05 kilonewtons per square metre, but that's compared to 0.15 for a simple OSB floor. So it's a lot heavier, but because it's heavier, it's harder to, the phrase we use is excite it, to get it moving and get that vibration. I'm not as slim as I need to be, but I'm a fantastic example. If I jump on the floor and it's solid, it's good. Some dainty wee runway model jumping up and down, pointless. Me, yeah. And if I'm telling you it works, it works. The problem with that, I'm going to go to the lecture in a minute, the problem with using that, this wet screed, 55mm, it takes 2 or 3 days to cure. 2 or 3 days. The OSB plywood takes 10 minutes. 10 minutes it takes to fasten it down. When we're talking about domestic extensions, single-storey, 2-storey extensions, that are completed, decorated, carpeted in 3 weeks. 3 days of floor on office buildings, etc. It's a massive increase in the programme. But it's not all about the programme and all about the speed. This is as engineers and designers, about the professional team. It's not just you, which you need to remember when you're out there. It's easy to be, I'm the engineer and we've got to work together. It's about the whole package. So we've got to think about what the user wants at the end of the day and what's going to be best and how much it's going to cost. And cost isn't just material, it's interest on the loans people borrow to, so if we're 18 months for traditional build or 6 months for ours, there's a massive difference in costs for the insurer, for the, not insurance, for the interest. So it's things like that we need to consider. But then if we're putting so many days of floor on top of that, again, those interest costs are going up. So there's the swings and roundabouts. There is another solution which is highlighted in here, which is a screed board. This is like a cementitious board, 12-15mm thick. And they're normally tongue and groove, so they interlock together like clip-lock flooring, with what looks like a thick walking fleece underneath it. And you just put that down, screw it down, but put it down on top of an OSB floor. So you're getting some increase in mass, some fantastic acoustic performance, some improvement in floor vibration, but you're still getting speed. That might take half an hour to lay rather than 15 minutes, but it's still a lot less than 3 days for the screed to cure. But you're getting that increase in mass, not as much as the 50mm, but... And again, when I walk on those floors, it's nearly as good as the concrete. Very, very, very nearly as good as the concrete. Like, you're really splitting hairs at this stage. But it's so much quicker. And the reason I'm quite positive about that, and there are 2 or 3 companies making that product, so I don't need to mention names, they're easy to find. I did a student accommodation job in Birmingham, very close to the Cadbury factory. I had to go inspect it and somebody else took over and make sure it was okay for the client. And I was designing some student accommodation up in Durham. And the client said, oh, we've found this new product we want to use, and I've got to redesign the whole building now because you changed the floor weight, which, you know, it's quite a big change that, isn't it? It's suddenly increasing the weight of the structure. So it meant everything apart from the roof had to be redesigned. But then when I walked on the floor in Birmingham, from the OSB that they'd previously, it's a lot better, I'm not worried about that. I walked into a room that they'd boarded, not plastered, but they'd boarded the inside and put the floor down, shut the door, and my ears nearly hurt, it was so quiet. And this is in the middle of a building site. So it really does work. And this is what I say when some of these figures are between a whisper and a shout. It means nothing. But when you experience it, if you get a chance to go on a site, I can't recommend it enough. If I can find a site in London that I can get you all invited to, I will do. But we have, as we say, how quick it is, but quite a short window when there's something to see between the structure going up and it being covered up. And once it's covered up, you could be anywhere looking at anything. It doesn't really matter, does it? So I will liaise with the professor and try to find things we can show you. Okay. Before I move on to the next slide, we do talk here about assembled prefabricated panels. The C-sections that traditional light steel framing would be Metsec, a household name brand almost, and they used to just supply what they refer to as, and the industry refers to as, random lengths. So about 3.2 metre long lengths of C-section that you would cut up on site and make to fit. And that's fine, brilliant, that's how office walls partitions are done, but in its baby brother sister, they're 0.95, 0.6 mil gauge, they're really thin stuff, isn't turkey foil thickness, quite literally. And that's great, it's still relatively quick. The alternative is that we use, and with that you've got a track section. You can all see that side, I'll try to stick over here. You've got a track section, and then you've got the stud fitting inside it, and I've tried to highlight that we've got 2 mil extra thickness. So when we put plasterboard on, you see the kink? It's not ideal. Yes, we can try to cover up the skirting boards and things like that, but it's really less than ideal. There are a lot of manufacturers now, mostly smaller ones, but there are quite a few bigger ones like Hadley that do something like this. And I'm ignoring the lips for the moment just for clarity. They squash the ends of the stud when they manufacture it. They crimp the ends in, so that when we board it, it's nice and flush. Yeah? So not all light gauge steel is manufactured the same. In addition, with this lip that I've ignored on the sketch there, we have a 10, 15mm, depending on the sizes, lip. But you've also got this C-section going inside it, so how does that work? Any thoughts? Yes, we're crimping the ends in, but we're not. That's 1 mil, 1.2, 1.6, we're not talking 15 mil crimps. Any thoughts? What we do, we knock the lip. Part of the manufacturing process, it just cuts that little bit out. This has several advantages. A, you can put it together. But B, with the Metsec idea, 3.2 metre lengths, put it on the floor, mark it out, etc. And come on, put the studs in, you can measure every stud, 600 centimetres or whatever it is. With this,
you know exactly where it's going. You cannot put it there. It's got to go there, that's it. And what they also tend to do, which I haven't shown on here, is the dimple.
Is it possible to show at some time, like, how the stud look like?
I'll try to see if we've got one
So
in
we
there.
can figure out the...
So we have this dimple so the screw heads are hidden away as well. Again, I'm not sure if there is one in the presentation. No.
Like any section,
Yeah.
any 600 section gives.
Yep. See if we can find something in here. There we go. So what we tend to do, the best way of doing this, is to assemble the panels in a factory, ideally. You can do it on site. And this is an example of the Lewis decking. You can just about make out the trapezoidal profile. So that, when we're manufacturing this, we're not cutting 3.2 metre lengths and cutting a bit off. We roll, manufacture the exact length to the millimetre that we want. And we can punch service holes in, so we can put the wiring and plumbing, etc. through, which makes the next stages far easier. All the power points, etc. The wires can just run through and come out to a power point. You then take those panels to site, assembled like that, stand them up, brace them, job done. It takes minutes, 5 minutes, to erect that panel, brace it, hold it down, compared to the time it takes to measure it out, etc. It's still going to take some time in a factory, but you're not messing about measuring it, checking it, making it all line up. The one thing we need to be careful of when manufacturing, these aren't brilliant with the joints are and things like that, but the joint isn't doing anything, it's just holding those studs in position. We need to make sure that the stud sits into the bottom of the track. Why might that be important on a 30-storey building or a 5-storey building or even 1 storey for that matter? But why will it be important that we have the stud bearing into the bottom of the track? Any thoughts? If, as I showed, we have the dimple for the screw, there's a screw either side of this to hold it in place. This stud, it's 150mm deep, that way, will carry somewhere in the region of 150 kilonewtons, 15 tonnes, as stud. Like I say, we can do 30-storey building, we think how many of these studs there are, it gets to be quite dense, or strength dense, if you see what I mean. The screws fastening together, in 1.2mm gauge, have a capacity of 3.2 kilonewtons, not 150. If we go to 1.6, they jump up to 5 kilonewtons capacity. So we have 6 to 10 kilonewtons capacity in those fixings, top and bottom, 12 to 20 kilonewtons. If we're loading this stud up to 150 kilonewtons and then it's not bearing stud to track, it will bear stud to track. With that kind of load, it will just, and it's not going to go far. If you can fit a cigarette paper or a piece of paper in, it's not going to go far, but it's either going to go with a bang or it will gradually go. Either way, you're going to end up with cracking around the room, which isn't good. If you were in accommodation and you've got cracks in the walls, you'll be complaining to the landlord. So this is why we need to be careful about these things. It's just something to look out for if you're involved in light gauge steel. Just make sure that the machine they've used gets that and the people assembling it have done that. Unfortunately, I was involved in one job after the event for a large main contractor. They'd had a wonderful topping out ceremony. They had 12 directors on the roofs, passed themselves on the back. A couple of hours later, the roofer dumped 5 tonnes of roofing materials on one spot, which they shouldn't have done. and then a 3-storey collapse. They had a 3-storey collapse because on Friday afternoon, people putting the roof on, oh, we'll do the fixings on Monday. So the roof joist, kind of, not on the, it wasn't this job, but they sat here on a Z hanger, literally an L, goes on the top, comes down and out. Once you put fixings in, we're then reliant on that 3 kilonewtons, 5 kilonewtons bearing capacity, so we can't straighten out without failing the screw. But if there's no screw in, then you're just reliant on the strength of a 1.2mm gauge Z not straightening out. And when somebody drops 5 tons over a metre kind of area, that little Z just gave up the ghost and took 2 floors out below as it went. There was a heck of a hullabaloo because they had 12 very senior directors stood up there hours beforehand, and from their viewpoint it was a near miss. And not just staff, it was the directors, so they really got very, very, very excited about it. And reasonably so. So again, when you graduate, you're out there, you're doing inspections, your site works, just have a look. It's daft little things like that. There's not much difference between a really good job and a really terrible job. A 5mm self-draw, self-tap screw. Yeah, it's fantastic. It really works really, really well. Screed on, etc. It's rock solid. Put the fixings in, it's rock solid. There are, what the word, kind of cases, stories of people who've gone to exhibitions, trade shows, built 2 or 3-storey buildings, which is quite common within an exhibition centre. Then at the end of the show, everyone wants to go home in a rush, like now, Friday afternoon. Often it's Sunday afternoons, it's even more. So we're not taking this with us, we'll just rip it down. Get some equipment, or pull the wall out and it'll just collapse in on itself. Nope. Square building, take 2 walls out and it sags a little bit. That's it. It still stands there. Progressive collapse is something we're going to talk about, and cover with all this later. But it is, when it's done properly, it's fantastic. But if it's not done properly, like any construction, concrete with the right mix, without the rebars, etc., bad welds, it's very dangerous. It's not a light gauge steel thing, it's construction generally. It's just, it is easy to get wrong. So, the Professor's just saying it's new. The other thing I forgot to mention is modules. We can do modules, not just panelised. But Romans had pre-panelised forts, pre-assembled forts. Eiffel Tower, we all know the Eiffel Tower, that was pre-manufactured. It wasn't fabricated on site. And post-World War II housing. Post-World War housing, maybe not the best example in terms of it wasn't designed to last that long, but it's still there, and it's now looking a bit shabby, but that's sort of the point. It wasn't supposed to last that long, I'm not that old. The people who designed it didn't design it to last that long, and it still is. So imagine your generation designing it properly, thinking about life expectancy and how long, and U values, and it's going to last forever, isn't it? There is guidance from people like the Steel Construction Institute, the SCI, and the steel manufacturers on how long light gauge steel will last in different environments, swimming pools, coastal environments, in a building. In a building, like this, you can't see on here, I know, but we've got the plasterboard, stud, a cementitious board ideally, insulation. The studs are in a nice, warm, dry environment. Fantastic, lovely. It is not effectively inert, it is literally inert. It's galvanised, it's weather protected, and it's sat in a warm, dry environment. There's nothing for it to react with. It will last forever. Okay? We can then, because of that, and with more modern technology, which I don't think I particularly cover in this, but augmented reality that people like Trimble are developing, have developed, and are using. We can identify where the services are on a finished building. We can see how it's supposed to have gone together with the golden thread, which I'm sure you've heard about, and post-Grenfell, etc. We can identify what things are. We can disassemble it quite easily because it snaps together like I often describe it as Technic Lego or Meccano, or the love child of Technics and Meccano. It's fantastic from that sense. So it's reusable, it's inert, it's very safe and stable. This, by the way, for the purposes of this, is effectively a module. You know, McDonald's restaurants, you can call it that. The record for putting one of their restaurants together, from breaking ground, people digging and really turning up, to flipping a burger. Any guesses to how long the quickest we've done it? Month. Any other guesses? Anyone? Any thoughts? Go on, have a guess. 2 weeks? A week? Hours? What? The record is 24 hours. The norm is 3 days. So this effectively is a module. It's brought to site, side beam, joist, walls. Yeah? This is from the 1600s and it's a grain store. These are not piles, they're to stop rats. The mushrooms, stone mushrooms. The idea is that the air can get underneath, dry the grain out, and the rats can't get over the top of the pile, over the mushroom to get into the grain store. But it's from the 1600s, so all due respect, it's not new. Okay? If a Roman centurion magically appeared on a construction site today, they would know what we're doing. Things have not changed. I'm nearly 50, I'm reliant on you lot to make these changes, please. I've spent 20 years pushing this, and I'm hoping that people like yourselves can encourage us as an industry to move forward. So here I'm going to quickly list 1837. Henry Manning exported cottages to Australia. Oh, not new. Okay. Eiffel Tower, as I've highlighted there, it was temporary. Yes. You know, just because it's temporary, just stopping at the start of the Second World War time, from 1908, people were selling houses from a catalogue. Okay, pre-designed houses. Again, it's not new. We talk about lattice trusses at some point and all. This is a way of making floor joists. If you look around most stations with their lovely arched roofs, they've got wrought iron lattices. It's not new, we just rediscovered it and rebadged it. We're not that clever, we're just trimming ideas from the past. Still going on, this IKEA and Skanska started making houses again, just like in 1908. Nearly 100 years later. We've reinvented it, we've got this new idea. Look at the grain store. No, you haven't. 2001, I joined.
2010, I talked about 30-storey buildings, 57 stories, modular building. 57. Well, I wasn't an engineer on that, even I'm a bit bold. And also, 19 days, I'm talking about 3 weeks. It was my house, and we've done one in Ireland for somebody else since. There's an extension to the side of the house in 3 weeks. I'm playing at it. Slightly less. They could do a 57-storey building. Yeah. I'm glad we're not that good. Yes, and finally, Ilka Homes. You may have heard of them. They've been on BBC News and things several times. They started up their factory at Flaxby, which is a hamlet, 5-6 houses, and an industrial park, just 2 miles from my door in Knaresborough. They're a fantastic case study there. Yes, they're losing millions of pounds a year in debt, but it's getting less and less each year. They're not here for the flashbang. They're not quick bucking out of it. There are several people, companies you will find, I was talking to the professor about it earlier, like the Gold Rush. People, there's a certain personality type thing, there's easy opportunity to make money. And they'll rush in and try and do that, and that's happened with quite a few modular house builders and modular manufacturers. No, it's not. We need to think about this in the same way that the pharmaceutical and the car industries think. It's going to cost you millions to develop the new car, tens of millions for new drugs. The construction industry just wants the money back now. We need to have a slightly different mindset in lots of ways, but particularly around the money. And those people who come in thinking they can make a quick buck, yes, if you know what you're doing, but they wouldn't do the same with pharmaceuticals, they wouldn't do the same with cars or any other manufacturing process, so it's a bit of a bugbear of mine. I'm going to flick through a couple of examples. This is a travel lodge. It's in Clapham. So I have to excuse my northern ignorance of London. I can't remember if that's north, south, west, wherever. Here you go. I do apologise. Once I came down to London, and maybe you can help me with this. A couple of years ago, I was walking across one of the bridges near the House of Parliament, right just before the Olympics, and there was an Apache helicopter flew down the Thames. It isn't a dream. I don't do drugs. It was so close I could see the pilots, the whites of their eyes. It was fully loaded with missiles, etc. There were 20, 30 other people on the bridge. Nobody reacted apart from me. I felt like a proper carrot crunch. I was like, is this a 3 o'clock fly past or something? Is that normal for here? No? No, that's fine. These were concession stands at the Olympics. I was fortunate enough to be involved in quite a bit of work at the Olympic Stadium. These are modules, so they're pre-finished, or as finished as they can be, and were brought and dropped around the outside for t-shirts, fish and chips, beer, etc. Because of the nature of the project, it was a bit like the countryside code of take nothing but pictures and leave nothing but footprints. We couldn't puncture the floor, we couldn't hold this down. So normally you've got a building and like a racing car, go around the corner and it tries to flip over. When the wind blows on one side, it tries to roll over. It doesn't actually try to roll over, it's heavy, but you kind of get the idea. We have to restrain it to stop that happening. But we couldn't fasten to the floor. It's lightweight steel, there's not much in it, so relatively the forces that we're talking about, wind pressure and the self-weight, it was quite an intellectual problem. Any suggestions on how we stopped it moving? There is the theory that it could literally
slide across the floor if there isn't enough friction, and it can also blow over. Any thoughts? It was a little out there, but also being a tight Yorkshireman, it was quite cheap. No? Put water tanks in the floor to increase the mass. The floor was 300 ml deep, and we just put water tanks in, knowing that if something happened, water would leak out. It's just water. If we put sand in, how to get rid of the sand? At least the water would just go down the drain, etc. So that was vaguely interesting. As I said, we weren't allowed to puncture the floor, but not that particular one. One was 30 or so. We were told, no, you can't put that down there today. Come back tomorrow. Why? Well, see that big torch in the middle? It's going to be lit all the time. Yeah. Can you see the gas pipe for it? No, neither can we. We've got to put it in. This was a week, 10 days before the opening ceremony. They forgot the gas pipe, the Olympic torch. So they dug a dirty great big trench, filled it all in, and then we could put the module on top of it. 2 days before the opening ceremony, we got a panicky call to say, we haven't done the seating in this corner of the swimming pool. Because everybody else thought somebody else was doing that corner. They thought that or that, and nobody's done it. It was amazing it all came together in the end, but the speed we can manufacture this stuff and do it, we did things like the director's box in the top of it all. It was a fantastic job to be involved with. But yeah, it was. This, I've forgotten exactly where in London, I've just forgotten the name of the place. This is a vertical extension to an existing building. Lots of lovely glass opening, but we have got columns, so we have to allow for those sort of features. This one, lots of nice cantilevers and other lovely features. All light gauge steel. Did have fairly thick concrete floors and a few hot roll beams to support it. That was in Brazil. The owner was a client of ours. Owns a company who made light gauge steel. This was his new family house. We stopped working together because to avoid paying tax in Brazil, which is 40% when he exported things or bought things in, from outside Brazil. He kept paying us in cash, which on the one hand is great, but when you're walking around with a couple of £1,000 in your pocket, even my size and bill, to go pay it into the bank. And he was avoiding tax in Brazil, and enough's enough, we don't need any work, it's not that good.
What you're saying, because you have to put it
I won't tell you his name. I understand why. It was, if you paid an engineer in Brazil, it was £10,000. If you paid me, it was £14,000 because you had to pay tax on it to keep money within Brazil, which I think is a brilliant idea for Brazil. But I just wasn't comfortable walking around with that kind of money. It happens to be the same client, but it's just a fantastic photo of. This is a portal frame. You know what portal frames are. When I say it's a portal frame, it's not a portal frame in the sense you would think of a portalised frame with moment connections everywhere. This is all pin jointed, and you can see just some of the connections, the forces have got quite high. We talked about 3 and 5 kilonewtons per fixing. Some of these have got 15 fixings at either end, so we've had to plate the connection to get sufficient fixings in. Fixings have got to be so far apart and so far to the edge, etc. But it worked. The walls are about, from memory, 1500 millimetres deep. So this again is part of the price of paying it. When you look at it on plan and take the area that way, it weighs somewhere in the region of 3 kilograms a square metre for the whole structure. rolled steel building, portal frames, 254 columns, etc., would be nearer 25 kilograms a square metre. Up to 15 metres, these are quite good. They're a lot cheaper, a lot lighter, and the columns aren't too big, and the rafters aren't too big. Compared to hot rolled steel, over 15 metres, and hot rolled steels, because there's only certain sizes of hot rolled steel, you can't go any lighter, any smaller, so they're over-engineered below 15 metres just because they've got to be, whereas this sort of thing comes into its own at that stage. We've also done work in Mongolia on a gold mine, and I forgot the other building we did. The gold mine was to house things like, you know, the big yellow Tonka trucks. Children have the big, you know, the kind of quarry dump trucks that you see, and I can stand inside the tyre, inside the wheel. Yeah. The garage for those. Then they had a workshop, then they had stores, and they had accommodation. So what do you think they built first? The garage, then the workshop, then the offices, then the accommodation. This particular part of Mongolia is 3 hours from the nearest hint of civilization, -20, and there are people sleeping in shipping containers while they built everything, and did the accommodation last. Yeah. But trying to get hot rolled steel out there 3 hours from the nearest village, not even the town, the nearest habitation, trying to get hot rolled steel was a no-no. But what they did do was put a rolling machine in a shipping container, not the one they were sleeping in, and several tons of coiled steel, took all that out, and then from that they could manufacture things like this, and the rest of the buildings that they did. So for them, I think the columns on that one were 3 metres wide. They were huge big things, but they were 30-metre spans. But they could do it, which was the problem. They couldn't do it any other way. They were carrying barrows with 2 handles, like a stretch of concrete for the foundations, and setting fires in the ground to warm it up, and it was a real challenge. It was full-on cold winter weather, Arctic sort of gear to live and work there, but we can do it in light gauge steel. This one is in York, and it genuinely is light gauge steel. It's clad with reclaimed bricks, but the inside, the inner leaf, the blockwork as would be, is light gauge steel. And again, referring to the speed, the brickies couldn't keep up with the steel. The steel went up like in 2 weeks, and the brickwork took 4. So the steel is the quickest part of it. York's a fantastic place, but one of his little foibles, planning-wise, is that the face of the building has got to reflect the look and style of the buildings across the road, or opposite. So at least some really fascinating architecture, really modern face, very traditional stone, but that's what you've got to do in York. This is a normal residential street in Fulford, south side of York. Yeah, but we can do it in light gauge. So the finish can be whatever you want, or whatever the architect or the team want it to be. We're not reliant on a finish. You can see the Travelodge, you can see the Brazilian house, and the York one. There's quite a range of finishes there, weren't there? Right, so coming back to a slightly more boring engineering-y, what do we need to think about? I've mentioned vibration, I've mentioned acoustics. We need to think about self-weight and the imposed load. If you go for your chartered engineer exam, especially with instructee, you have to design a building as part of the exam. And I remember one colleague talking to me about when they did it. They were told, house, this is that. Right at the very end, he said, oh, by the way, it's on sand. They hadn't read the question, they designed it all in concrete, and got to the end and just, oh, that's not going to work. One of the things, so when you're thinking about design, think about the self-weight, how heavy it is, what it's doing, what is it, a classroom, is it a lecture room, is it a gym, is it domestic loading, etc. What kind of loads we're talking about, but also think about what you're building it onto. Okay? Fire is, excuse the pun, a hot topic, particularly at the moment, isn't it? The Grenfell Tower reviews just finished, etc. That's kind of come back to the fore again. Is it Mr. Gove has been banging the drum about developers doing a better job and taking responsibility and not being able to hide from things. Fire is a pet interest of mine when it comes to light gauge steel. There are several issues to be kind of wary of. The main one with fire and testing is the inability of the test houses to really test. I know, it sounds a bit strange and what? I've had long conversations with BRE, Exova and another testing house, and the maximum load they could, might be 3 years ago now, things might have improved but they haven't told me if it has, the maximum load they could put down, a stud in the test rig, was 30 kilonewtons. 3 tonnes. Now we talked earlier about 150 kilonewton capacity. When you, as interested as I am in this, and you read through the standards and the guides and that, one of the clauses in the testing standards is that as engineers we cannot apply more load in our calculations than we have tested. Sounds quite fair and reasonable, to be honest, until you get to that 35 kilonewtons test load. But they still can carry 150, and we're doing nearly 60-storey buildings in China, 30 stories. The forces are a lot more than 35. 35 equates to about 3 stories of domestic housing. So there's a bit of a problem there for me, because we can't apply more load than we've tested, but we can't put more load on that because that's all the tests we can do. Yeah.
Why don't we test higher? Is it because we don't have the facilities?
That's what I'm trying to say, yeah, the test rigs from BRE, that's all they can apply.
Yeah, it's a business.
So, yes, the people who helped write the standards, they were government, now they're being privatised, not politics, but they were the building and research establishment, they were government, and even their rigs, mind-blowing. So, as part of all this, and working with not just Professor but other academics, and manufacturers, we've gone a little bit further and found other standards that allow us to calculate the capacity of a stud. We all know that if we heat metal up it gets soft. Yeah? We all accept that. So there's, at its most basic level, the idea that you either just heat it up like rapidly and it gets to a certain temperature and it softens. But equally, if you put a lower amount of heat but over a longer time, the heat energy still amounts to the same, so you can get this softening effects as well.
So it's important we know A, the temperature, and B, how long it'll last. If we were to load a stud to 149.9 kilonewtons, knowing it can carry 150, and then set fire to it, or you don't want to set fire to the stud, it's metal, you get the idea. It's going to last 2 or 3 minutes. So it'll get that little bit warm, lose that little bit of strength, and it'll go, because it's so close to failing anyway. So you can do like some manufacturers do and put 14 kilonewtons down the stud. And then it'll stand there forever. Well, not quite forever, but it'll do 2 or 3 hours. And you've got a 2 hour, 3 hour fire test. Until you look at the load that they've applied. And that's like a story and a half of housing. But I've got a fire test. And to some people, right, tick, job done, got a fire test, moving on. Yeah. It's not quite right, is it, as engineers? But to some engineers, yep, fire test, next. Don't want to rock the boat. I don't want to rock the boat, I don't like upsetting people, but equally, I've got children who are, the eldest one starting university next year. People like yourselves, I don't want you or my children living in accommodation that's not safe. Because, well, we've got a fire test. That I'm doing what I can to change that mentality. That's why I'm talking to you about it today. And I am quite vocal on social media and in the industry about it, and have a slight reputation for being a bit a man-like. People like me for being that honest, and others always trouble causer. Oh. So yeah, we can now calculate stud capacity when it's hot according to a standard, and that's great. But what we don't know yet, or we struggle with stupidly, is how long it takes to get hot. So we put 1 or 2 layers of plasterboard, and it should be easy to calculate the U value effectively of how long it takes the heat to get through the studs and the stud get to a certain temperature. And there is the argument that if you've got the boards this side and this part's getting hot, how long does it take to get to the other side, etc. You've got a certain amount of time to travel across. So what we do, or the suggestion is that when we test any stud, whether it be facades, non-low bearing, low bearing, etc., we can measure the temperature in the fire, in the furnace. We measure the temperature of the flanges of this hot side of the stud, and if we take that temperature and assume that the whole stud, which is what the standard does for calculate the EN 1993.1.8, says that if the stud gets to this temperature, then we reduce the yield strength by this percentage. So rather than, well, it's taking so long to get through and the average, no, we'll just measure that temperature, use that. It's crude, it's simple, it's simplistic, but it's something. We can calculate the reduced yield strength. And the good news from our viewpoint is that as well as reducing the yield strength from 390 to 200, typically, or even less, we can reduce the load factors and the loads that are on there. Partly theory is, if there's a fire, are we all going to sit here and wait to be rescued, or are we going to get out of here as quick as we can? The latter, isn't it, I'd like to think, under normal circumstances, other than being equal, yada yada yada. So we can reduce the load, because people will go. People will not generally sit around waiting to be rescued. And there obviously are exceptions to that, but that's how the standard works. So we can, as well as reducing the capacity, we reduce the load that we apply. So it's kind of swings and roundabouts. And it works out using that whether it's in the fire state or a normal cold state check as we do normally, they kind of balance out. The reduction in capacity and the reduction in load factor, the ratio of strength is about the same. Coupled with, on floors and facades, it's deflection that governs the design more than strength. It's not that big a deal. But it is something to be aware of, something that's becoming more and more prominent. There are answers, there are solutions. It's not, okay? Wind is not our enemy, but is the biggest thing we have to design for normally. You impose loads for deflections for floors, etc. Yeah, but wind, whether it's going to knock the building over, the bracing we have to put in to resist it, how we resist the racking resistance. We can look at sheathing boards, plasterboard even, OSB plywood like we do in a timber frame building, the cementitious board that we talked about. The cementitious board is my preference. It's very, very, very hard. It's difficult to drill. When I did my own extension, I did slip and went through my finger. So I know it's not easy, but it also stops rats and other vermin. So when you've got these lovely water pipes and wires in the walls, in the service holes that we talked about, and the mineral wool insulation, if people put that in, some people do put it in between the walls to help keep the vibration and the sound down, they love it. It makes fantastic nests. But if we put cementitious board, you can't get through it. Put OSB and things on, they can in days. So there's advantages and disadvantages. It's not the nicest thing to be thinking about, but it's reality, it's practicality. It's what we do, isn't it, as engineers? So yeah, winds. The other solution is to put K bracing in, diagonal. When I've talked about lattice trusses like on train stations, the diagonal, if you put that through 90 degrees, yeah, we can have that to resist the lateral loads. I could do a whole lecture on that. I started reading for a PhD myself on racking. So I can bore you to tears on that one. So we'll leave that for today. Vibration, we talked about how lively floor is, how prone to vibration. It's the same with lateral loads. If we get it wrong, it can be rattly and not so good. And acoustics. We design this nice solid building so that it feels right. Therefore, it's solid and will transmit the sound perfectly. Like if you hit the radiator, you can hear it upstairs, can't you? The sound goes through the water pipes, etc. If we've got the structure so stiff that if somebody hits the wall, hits the floor, jumps, your 18-year-old son plays guitar very loudly, you can hear it everywhere, unless you stop the sound getting into the structure in the first place by putting mass, plasterboards, gypsum boards, other solutions onto the things to stop the sound getting in there in the first place. So again, for every problem, we've got solutions. The 2 layers of plasterboard, difficult to fit, it's time consuming, it's etc. It is. No defence to that. However, we can use it for the fire. We can help with the acoustics. We can help with the wind and the racking. We don't want to silo the design. I'm a mechanical engineer by training, as it happens, but I'm working as a structural engineer. I'm not just a structural engineer, I'm not just doing my bit. I'm working with the architects, with the services, the M&E, with the acousticians. We have to come up with a solution that suits the job, not just my bit. Yeah? If you take nothing else away from today's lecture, please think about working with other people, as in the rest of the professional team. It's very easy out in, not the real world, but out in work world, to be, I'm doing this is my job. Blow them. It's not the best thing for the client. We need to work together. Ideally, they want to sit down at the start of the job rather than halfway through and solve these things. And this is how we did it last time, and can we improve on it, etc. So, again, if your generation, I'm old enough to be a dad for most of you, to be honest. If you can make that change that my generation haven't, then I've done my job. I can kind of not die happy, but you know what I mean. I feel like I've done something. I'll have left an imprint on the world if the next generation listen. Forces, buckling on moments. Okay, it's light gauge steel. I talked earlier about the dry lining studs and how they're almost turkey foil, which is true, probably this time of year, but it is ridiculously thin stuff. If you take a stud
It's very slender, not like me. It'll buckle, it'll squash. So when we put the boards on, and they're fastened on at 150mm centres, they provide enough strength to hold it steady so it won't do that, it won't twist. I like to use a plastic first image drill at this stage. If you hold the ends and push, it doesn't just bow out, it'll twist down the length. Even plasterboard, soft as plasterboard is, has sufficient strength with the fixings at those centres to prevent that twist. It's the same, by testing, as putting a restraint, we call it a noggin. I didn't make the word up, that's what we call it. We put a noggin at halfway up, so 3 metres, 1.5 metres, halfway up the stud. The plasterboard does the same thing. So you can reduce the effective length by a half. If you start using things like cementitious board or OSB, we can get even better, like 3rd and 1/4 point restraints. It fully restrains the stud. So, as well as providing the racking resistance and the fire protection, it can also make the stud more efficient. So this is what we need to think about, the whole, not just the one bit we're looking at. And so it becomes a system, even within, like within it's a system itself, not just a module or whatever else. It's
So, do you have like a standard system that you follow for each job, or like according to the...
This is the kind of closest we have to a system. How long before we want to have a break, Professor?
Let's break in 5 minutes for...
That's fine. I just don't want to...
And then we'll have
So I'll talk about this now, and then we can... The other huge problem for the industry is there's no standardisation. I have a spreadsheet on one of our on the MMC website which lists all the manufacturers that we use in the software business and all their profiles, 100mm stud, 200mm studs, etc. And all the different flanges, and all the different lips, and all the different yield strengths, or for each profile. There are something like, out of about 1,000 profiles on there, I think. It's something like 60 different 100mm studs. So studs that are 100mm that way. Some are 38, up to 60, and it's almost in millimetre increments from different manufacturers. Then we've got the lip, again between 10 and 15mm, and then there's yield strengths. Some are using 350, some are using 450, and anywhere in between. The industry has this real problem with sharing information, including fire test data. It's very secret squirrel, that's ours, we've paid for that. I understand that, yes, we've paid for it, but then when we, the industry, start talking to clients like government about the government want to build 10 hospitals, for example. Brilliant, fantastic. We can do these in record time. Yep, yes you can. So you've got a factory, you've got a factory, and you've got a factory. And you all three do 100mm studs. Yours is 100 by 38, yours is 100 by 40, yours is 100 by 45. So when it comes to putting sections together, the junctions, the details, etc., you can't swap your studs round because they're subtly different. They're the same wall depth, so on floor plan things, that's no work.
Just go to the next slide. Because it shows actually how it looks like.
Yes. You can see there with the different sizes, etc. But if they go with you, because the design says they go with you, and you spend all that time and effort doing all that, then the QS comes along, quantity surveyor and says, well, if I go with you, I can save 10% on your prices. Even though you've got all the fire test data and the architects and designers who are happy with it, but that's how the QS gets his bonus, or her bonus. That's how they get paid. Right, so we're going to go with you, save 10%. Fine. Annoying, but that's life at the moment. Then aliens destroy your factory. Halfway through the job. Now what's government going to do? They can't go to either of you two because your studs don't fit. So government look at it and say, nah, it's not worth the risk. Not of aliens, but you know. The industry is going to stay as this small cottage industry until it gets together and starts to share and be a grown-up about it. I often describe it quite rudely as teenagers. And we're trying to get it from 14, 15 to its mid-20s. It's that, we can just bridge that gap. It's almost like a blood sport. We'll go to meetings and suggest standardisation of profiles to the manufacturers. And the heads explode, the air goes blue. Do you know what's that will cost? That's going to ruin. Manufacturers love having their own profile and getting into bed with clients and almost like golden handcuffs because they can't go next door and save 10% because they're stuck with your profile. So they're using that as that's great for us. But they're not seeing the bigger picture. Yes, they've got 5 schools with Wilmot Dixon. But the 200 schools the government are promising, they're not going to get a sniff at because government can't afford to invest on that scale, knowing that if something goes wrong, one of the bigger manufacturers, a company called Caledonian, went bust only in the last 18 months. And they've been going for 20 years or so. They were rock solid, they were, you know, safe, very, very, very safe. Like Barrett's house builders safe. But they went bust. If they can go bust, anybody can go bust. Government know that. Banks went bust, didn't they? So there are moves afoot within the industry to try standardise this, different ways of dealing with it. But as we can talk about later, there's then become issues with what do we standardise around. Floor joists want one thing, wall studs, low bearing wall studs want something else, and infill facade studs want other things out of the profile. They all have different requirements. So it's where we standardise. And you can't, very reasonably can't, standardise around your profile because that will upset the other two. No matter what the reasons are about your profile, how wonderful it is, we've got to find, it's very difficult to do that and make everybody happy. So, but we are trying, and if we don't, it's not going to die, but it's not going to fulfil its potential ever, the industry, in my opinion. Part of this then would be the fire protection, the acoustics. We could develop standardised solutions to all those around these. And there's nothing wrong with manufacturers having a core of standardised profiles and their own bespoke ones that they can save money on or offer advantages. But if they have these core ones that everybody can use and everybody can specify, just the same as hot rolled steel and masonry bricks and timber, they're all standardised profiles, so it works. But it's going to be painful getting there.
Yeah, what we usually say, if we can't standardize the product, let's standardize the process. So indeed, one of the biggest problems is the competition between all the fabricators that are coming up with different systems. Okay, so you can't really say that there is one particular that behaves better than the other.
No,
It's
absolutely
just that the quality surveyors is what you have near your project. There are a lot of different factors that they will play their role in going with a particular fabricator when it comes to this. But going back to if it's new or not, before we break, indeed, prefabrication is one of the oldest concepts. Everything is prefab, in fact. in steel construction, we have everything prefab. The difference is that you don't build on site like we do for reinforced concrete structures. Okay, so anything else, it has an element of prefabrication. But the new methods of construction, the modern methods of construction, they're more related to the way that you manufacture something. So we're trying to move away from the on-site construction to the off-site manufacturing concept, which is not new. Of course, it's not new for other disciplines. It's been there for donkey's years. But for us, for most of the countries out there, let's see what's happening in Europe, let's see what's happening in Asia. Most of the countries, they still build either prefab, a degree of prefabrication of steel construction, or mostly on-site reinforced concrete structures. Okay. So this, as you look at that picture, is more like as a systems approach, and there are systems of systems to what you were asking before. Okay. And that is the new mentality that you have to have when you start designing. That is the new thing, is the mentality of how to approach the problem, rather than the actual product. The product is prefab, as we all know how it can be done. Now, let's go for a 10 minutes break or something, because there's a lot to cover after that. So let's come back a bit before than quarter two. Okay.
Thank you for coming back. Right, so we've briefly discussed some aspects of this just before the break. I said, as part of it, very quickly, about self-weighting imposed and things that we need to design for. As I keep mentioning, there's this sheet you can download. I can send more to the Professor for you to collect from him. Or if I leave you my card, you can email. We can talk about that later. Different floor finishes, such as OSB, cement particle board, the one we talked about, the mineral wool, other built-up ones, and the self-weight, the concrete, etc., all have different weights. But what this doesn't mention is that different finishes, different floorboards of the concrete, and others in between, share the load differently. By that, I'm trying to say these joists and the board spreading over, there's a wall in between, but the 18mm board, when we design for the deflection, we put a 1 kilonewton point load in the middle and we allow it to deflect 1mm, dependent on the joist centres and a few other factors, which again, we can talk about in some detail a little bit later or another time. But we allow that 1 kilonewton point load to be shared over a number of joists, because as you put the point load on the board, it will pull down, but it will also pull down other joists with it. It won't just deflect between the joists either side. It's sufficiently stiff that it will pull down a number of joists along the span. So if we put the load there, it will pull this joist and this joist down slightly, and the ones further away it wouldn't extend to. Whereas other finishes like the concrete would share over 4.5 joists. Okay? So the floor finish, apart from the self-weight, matters when we're discussing the vibration. So it's important in light gauge steel, and that's why on the, I know you can't see it from there, we have the picture, description.
The next slide is called.
Oh, it does. We've got examples here of the fire rate and the acoustics. Sorry, not fire rate. They're both the acoustics, the airborne and the impact, and the fire resistance. What we've also got on
on the sheet is the floor type. And that sounds slightly ridiculous, picture the floor type. The floor type for how many joists it shares the load over. In the 80s, 1980s I think it was, Milwaukee Institute of Technology did some testing on different floor finishes to determine how many joists these different floors bring down, share, etc. And we came up with this: chipboard, cement particle board and built-up acoustic floor. And then for these spans, these are the amounts of deflection that were allowed. This then affects that vibration. So I'll say this was done in the 80s, and I joined very, very, very early 2000, late 1990s. Even this industry is slow to respond. So it's a little churlish when I complain about the rest of the industry not responding and Romans still recognising what we do, etc. But 20 years, not 200-300 years, so you know we're fairly fast. But that's what this is all talking about, and that's why we list these different floor types, not just from the acoustic and the fire viewpoint, but as engineers, the feel, the finish, the way it behaves itself. And this is where it comes from. It's empirical data, so we're having to do a little bit of interpretation of what a 18mm chipboard with isolated top hat and plaster Warburton top hat is. But as an industry, not my personal opinion, group of people have decided that these are what this classification is what these are, to make that a little bit easier. But in the SCI guide P402, which is the de facto guidebook for designing light gauge steel, it's not one of those if ever you're having trouble sleeping, read it. It's actually quite easy to read. When I say it's got lots of pictures in, that sounds really condescending. It's not a heavy, dry, boring textbook. It is a textbook, but it's not particularly dry. It has got lots of information and is really, really useful. I'm sure as students you can get a copy for free. If not, it's about £30 to buy. It's not a lot of money. But if you're involved in light gauge steel, I cannot recommend it enough. It is very, very useful. There are gaps in it, but the information that is there is really good. And when I say gaps, you're at the level I'm looking at and being picky. For anybody who knows nothing about light gauge steel, it's fantastic. So I really can't recommend that enough. This is just talking about those deflection limits again, but we've got dead and imposed over span over 350 or 15mm, and then we've also got the imposed divided by 450. That's the static deflection, and then the dynamic I keep talking about, because this is kind of the Achilles heel for light gauge steel. It's that feel. We get this issue with all manner of construction, not just light gauge steel. Without sounding any more middle class than I need to, walking in our local Marks and Spencers, it just happens to be, I'm sorry it is, the first floor of the building, even I can feel this kind of tremor. Very, very subtle, and you've got to be looking for it, but it's a traditional 80s concrete frame building, big solid concrete floor, and there's that many people walking around. It's just enough to get it excited.
to be able to feel it. I'm looking for it. Every building I go in, consciously or unconsciously, I'm looking for it because I'm interested, stroke paranoid, about floors deflecting and vibration in the field. But I say it's not limited just to lightweight steel. It's an issue for any form of construction. Like I say, something like that can have it. But when you're going into a building like this, you're often going in with people who are looking for problems. People my age and older who've always done it this way and don't want to do it, don't want to change, so they'll be looking for reasons not to. So I at least try ridiculously hard to make sure that there aren't any, that all those aren't there, so there's no excuse. They'll find something else, but just... So this is why I have to talk about this, why I go on about deflection so much. The 1 or 2 or 3 times I've been involved with floors either that I've designed or others have installed where there have been problems, it's 9 times out of 10, all 3 times it came down to the floorboard and the fixings. They'd used 12mm thick OSB rather than 18, it's 6mm, nothing. But it's a third less than it should be. So it's a third less mass, a third less strength, and it literally bows between the joists. You can feel a little bit of bounce, and it's not the joists, it's the floorboard itself. Or if it's not fastened down properly, 150mm centres at the end, which is about the height of this bottle, so every 150mm, and in the middle of the board, 230. If you're the one putting the floorboards down in a room this size, that's a lot of fixings. But if we don't do that, we're not going to get the composite action, we're not going to get the load sharing, we run the risk of it feeling funny. You can get funny tools, like a pistol drill with a long shaft, and it... so there are, ways and means of doing these sorts of things. When we talk about joists at 400 and 600 centres or smaller, any thoughts? Is it just it was a nice number? Is it coming from imperial days of feet and inches?
Nice round number.
Yeah, I think it's possibly a bit of all those. The main one today, and why we've got to that, is perhaps it's a nice round number and imperial measurements, etc. These boards come in 2.4 by 1.2. Sometimes, just to be really difficult, they come in 2.44 and 1.22. Because 2.44, 1.22 is 8 foot by 4 foot. 2.4 by 1.2 is the nearest metric equivalent. If we do these at 600 centres, 600, 1200, 1800, 2400, it fits. If it's a 2440 joists, it just gets to the edge of the board, so you can't get the next one on. So you're cutting off 40mm on every board in this room, and this isn't a particularly big room, is it? So this is why we have to think about this. It's part of this, everybody sitting down at the start of the job and thinking about it. And the QS, you just sat in the wrong place, I'm sorry. Well, I can save 10% if I buy these 2440 boards, they're on offer. Yeah, great, says the site manager, I've got to cut all those down now. Thanks. That 10% saving, we've spent 3 times that on labour now. So it's this stopping and thinking and working together. Yeah? So I keep talking about working with the rest of the industry, the rest of the design team, and I keep talking about the system. It's not just the light gauge steel, it's not just the engineering. We've got to think about, as a team, bioacoustics, thermal, and most importantly for me, how we put it together. As I said before, chartered mechanical engineer, loving doing light gauge steel. I've found my niche and what makes me tick. I'm thinking about a building and how we put it together, and I found my happy place, so to speak. But I come from a manufacturing background. Started making packaging machines as an apprentice. So I'm constantly thinking about how we manufacture it, how we make it. I have been a technician on the floor trying to do the impossible. Wish I've got a joint half out my forearm and things so I can get bolts in. It's ridiculously important. There's an adage, a rule of thumb about the 80-20 rule. 80%, 20%. 20% of the cost is in the material, 80% is in the labour. We make a massive saving on the materials and we save 10% on 20% of the cost, so that's 2%. If we make a 10% saving on the labour, that's 8%. So we don't want to be looking at the material so much. Keep a weather eye on it, it's important. But think about how we put it together. How is it going to make life easier on site, in the factory, for everybody else? It's not just about our bit, it's the whole project. Also to remember, especially things like housing, this is somebody's house. This is somebody's school, somebody's university. It's not just a job. As you'll find as engineers, I'm sure you do already, that the client might own it and the architect's designed it, but it's our job. We take a heck of a lot of pride in it, don't we? You point out things that you've designed. They're yours. I used to design lampposts up in Sheffield, there's some stainless steel ones still around the ring road. They're mine. I designed them. That's all I did. I didn't manufacture them, I didn't put them in, but I designed them, they're mine. And the same with houses and buildings that I've done, they're mine. So you've got to try and remember that, but ultimately somebody's living in this, so let's try make it right, not cut corners, etc., no matter what the clients say. As chartered engineers, we have responsibilities to society, the profession, then our employer. So, wall studs. I talked briefly about effective length, etc., and how we can use the different finishes. Acoustics I keep rattling on about. Resilient bars, everybody heard of those? No? They're like a Z. They're very shallow, about 15mm thick. They go between the stud, face the flange of the stud, and the boards. The idea being that they'll vibrate a little bit of sound vibration, so absorb it so it doesn't get into the structure. They're fantastic in a lab, testing, brilliant. On site, if the person putting the screws in gets it wrong and the screw goes through the boards, through the resilient bar and hits the stud, then you bypass the resilient bar completely and fail the acoustic testing. Yeah. But they sound brilliant. Sorry, bad pun. The tests and everything make them look fantastic, and they're relatively inexpensive, and lots of other benefits. Just to be wary that you need really good site control. People need to be careful with what they're doing. But other than that, they are fantastic. You've also got the double wall construction, so that the more space there is, the harder the energy will dissipate across the gap, and the mineral wool in between. Doing this with mineral wool between two studs, fantastic, absolutely brilliant. But thinking about fire, and we talked about it, or I touched on it briefly earlier, the longer the heat takes to get through the system, from the hot side to the cold side, the more heat energy the stud absorbs, the softer it gets. So rather than one big hit of heat, lower heat over a longer time, so we're baking it. That's what can happen with putting mineral wool between the studs. Fantastic for the acoustics, it dampens sounds, it makes it feel a bit more solid, not got that hollow-ish feel. It dampens all that out. But it can be at the cost of fire. And when I say at the cost of fire, it can mean 3 or 4 or possibly 10 minutes difference in fire rating. But when you're looking at 30 and 60 minutes, 3 minutes can be 10%. So it's just something else to think about. It's not a panacea. Equally, it's not the worst thing in the world either. It's just be aware. And when you're looking at fire test data, how have they done it, what have they put in, is it, etc. But it's fantastic for acoustics. One of the tools we've done in our software with this noggins, remember I talked about a noggin, a horizontal member to reduce the effective length versus the gauge, thickness of the material. One of the tools we put into the software is that it calculates the self-weight per linear metre of the wall. Because until 2-3 years ago when we added the feature, you'd sit as an engineer and you'd run the design and you think, well, I think 1.2 with a noggin at mid-height is going to be lighter and cheaper than taking the noggin out and putting 1.6 gauge studs in instead. I think that feels like that'll be lighter and easier because they've not got the labour putting the noggin in. I'm not sure. So now we've calculated the weight of a linear metre on plan of wall, length of the studs, top track, bottom track, and any noggins, so that we have a better idea as engineers. And it's actually been quite useful for others involved, the estimators, the QSs, that they now know how much it weighs and therefore they can price it, because they price it per tonne, or per linear metre, etc., or normally per tonne. So it's been a Brucey bonus. We get to know that we're producing the lightest design, and they get to know roughly how much steel's in the job without having to draw it all, etc. The other considerations are speed of manufacture, speed of assembly, speed on site. And we also need to think about whether we're modular or panelised. If we're doing modules, we might have that detail anyway between the modules. We have 1 module, 2 module, and we can put insulation in between. So we might get that as a bonus to it. But we've got 2 walls, so twice as much steel compared to a panelised system. But if we needed panelised system, or we needed studs at 300 centres, we can eke them out to 600 because there's 2 of them, the same amount of metal. So there's a lot going on in that mix, isn't there? It's not black and white. But you're all bright, intelligent engineers, so you can think about these things. The effective length we've talked about with the noggins, etc., it makes a massive difference to whether the stud will buckle, twist, etc., and different ways of combating that. But it's a factor. The noggins versus the gauge, again, the stockier, squatter the stud, the stronger it will be, the less chance of it twisting down the length as it's loaded. But if it's thicker, it's heavier. If it's heavier, it's more expensive for the material, it's harder to manufacture. Even going from 1.5mm to 1.6mm can be a large difference in the speed of the machine and how easy it is to manufacture, to form. 0.1 of a millimetre. I was a bit like, really? When they said to me, but 2 or 3 manufacturers have said the same thing, it makes a big difference. So The one, the eccentricity of the load from the face. If we imagine the C-section again, and if we're loading it with a floor joist that's sat on top, so if we have the stud and the floor joist like that, and the centre line of the stud, there's no eccentricity, there's no additional bending moment. We've already got the wind load, lateral loads, etc. We haven't got an eccentricity, an additional buckling force. But if we're on Z hangers, so it's on the side, it's at least half the depth of the stud over, isn't it? And the moment capacity, we talk about 150 kilonewtons axial capacity and things, but no, it can't collect itself. The moment capacity is normally in the region of 2 or 3 kilonewton meters. It's nothing. You look at hot roll steel profiles and they're in the hundreds. Light gauge steel can't really cope with bending moments. It buckles. So we want to reduce eccentricity if we can, but equally we need to be aware of it and check it. And so what I think is a reasonable eccentricity, just because, to be careful, 25 millimetres. That's on top of half the depth of the stud, it's just 25 mil. It's one of those things that you can, when you're engineering it, if you're in this position, knock it down to 0 and see how big a difference it makes. And a bit like with masonry, we're allowed to tell people to take extra care. Same with light gauge steel, tell them it's got to be close up, we can't have gaps. Incidentally, I was on a job a couple of weeks ago where they had put the joists and there was a 20mm gap overall. Worst case it was at both ends, but generally it was overall. And the floor was slightly bouncy because this Z hanger, just 1.2mm out, and the joist sitting on that, and it was just giving that little bit of bounce, albeit yes it's me jumping up and down on a 5 metre span. If I can't make it bounce, nobody can. But I was feeling it, just that tiny little bit, and it wasn't finished and there wasn't all the mass there and yada yada yada. So this eccentricity can be critical. We're only talking small numbers, but we're talking small profiles and very slender, delicate flowers, you know what I mean? So the stud centres, closer they are together, less load per stud. Roof load, floor load, and a number of floors all obviously impact the design of the wall. Self-weight, wind load, and limiting the deflection. We're limited to 360, height up to 360, so the height divided by 360, that's the amount of deflection allowed. If you go less than that, 250 or 180 you will do for a normal steel beam, the plasterboard will crack. Not might, it will crack, which none of us want. So that's why we specify that, but if you're doing a building that's not plasterboarded, not a residential type situation, we've got to go back and think about the fire and other issues, but you can then reduce the deflection rates and just rely on the strength checks. The only horizontal deflection this is really going to consider is the wind blowing on it. So here in the centre of London, wind load of 0.3, 0.4 kilonewtons per square metre. Out to Hebrides, 2 and a bit kilonewtons per square metre, more of a problem. It's just something to be aware of. So this is a very quick example of member checks. Again, for anyone that's interested, we have a full 2-storey house. Set of worked examples, the British standards on the Eurocodes. I'll leave business cards here if anyone wants to drop me a line after or ask anything else. I'm very, very open to
conversations. This is a British standard check. Buckling resistance, short strut capacity, Perry coefficient, buckling under axial load, buckling resistance, and then the overall buckling check. So checking the applied load, the short strut capacity, the local buckling and the moments in the x-axis and the local buckling, and this is the strength on the weak axis, and checking the short strut capacity in the weak axis in the Y. You can see a massive difference between the two. Strong in the weak axis. Again, compared to hot rolled steel, these are piddly capacities, but it's the difference between the strong and the weak axis. This is the student accommodation in Durham that I redesigned and actually quite pleased about doing when I walked on the floor. We're literally lifting boxes onto site, onto pre-prepared foundations, drainage, etc. They've scaffolded up around it so they can put the external finishes on when they're done. There's a bespoke lifting frame. We can design the modules so that they can cope with compressive forces, so we could lift from a single hook in the middle, the chains, etc., sloping in, and then design for the compressive forces at roof level, or we can just do a vertical lift on a bespoke lifting frame. Personally, I prefer to do it this way because we're not putting metal in for 10 minutes of its life when we're picking it up. We might as well invest in a lifting frame that can be used multiple times on the one job. If it's adjustable, it can be used on every job, and we're not wasting metal and resources in the pod itself. But as I've highlighted there, and we discussed with the McDonald's, 3 days is typical, 24 hours was the record. What I didn't mention is the 3 months in the factory it takes to make it. It's still a lot quicker than the year it would take to do it traditionally. But if speed on site is the critical thing, schools, for example, you want to do an extension in the 6-week summer holidays, there's no way you can do it traditionally, whereas we could spend 2 years off-site getting everything ready and then be done in a couple of days. For various reasons, for whether it be schools in the holidays or emergency shelters, any reason you just want to be done, gone. Lack of disruption. The very nice areas of London where people don't want the noise and disruption. Put screw piles in, very, very quiet. Drop the module and be gone. Hours. There's lots of reasons. Access, you need to think about. It's one thing getting a transit van in with lengths of stud to make on site. It's entirely another operation trying to get this behemoth in. 10, 15 metres long, I think is the maximum we can transport in the UK, 4 metres wide and 4 metres high. It needs a bit of space to get it in and to manoeuvre it around, doesn't it? So transport, and when I say drivers, I don't mean literally the person driving the vehicle. It's what are the reasons the drivers for doing a certain type of construction. Briefly touched on this already. But the main point is there are as many solutions as there are manufacturers of modules. It's the same with, and I know professors working on module connections, there are as many module to module connections as there are manufacturers, and there's no, I think you'll agree, there's no one, that's why you're doing it, there's no one perfect solution yet. Yet. I've seen some absolutely fantastic ones that solve 95% of the problems, but they've got one glaring issue. And I've seen some that I was like, why? But they like it. Customer is king. So there's lots of different ways of doing things, but there's also lots of things to consider. The LOLA, the lifting regulations, mean that lifting chains and shackles have to be tested and certified and not looked after, that sounds like looking after a baby. But we've got to trace them and know where they are and know that it's safe and everything else. Whereas if we lift it once, if we put a service hole on the top of a stud and then cut it off when we're finished, you don't need to test it, you just over-engineer it slightly. That's it. It's easier on site, it doesn't need quite so much control. So there's lots of different things to think about. I keep talking about Z hangers. Hopefully you can see the blue line. The blue line is this Z hanger. It literally sits on top of the wall, comes down the required depth and then out. And the joy of a Z hanger is they can be nearly literally infinitely long as you can manufacture. Typically on a press brake it's about 8 metres is the longest you would see, and after that they start getting a bit difficult to handle anyway, they start twisting them all in. But the main advantage is, well, several to be fair, when you put the roof or the floor joists on, whether the trusses or C-sections, they're all at the right level. Which sounds, yeah. If you put in hangers, joist hangers, you've all seen joist hangers on timber buildings? You know the sort of thing I mean, don't you? Joist hangers? Yes? No? Shake your head, nod? One or the other? Yep. They need lining and levelling, you've got to get them all at the right level. Whereas the Z, it is, for 2 or 3 metres, it's the right height already. So you could, I'm not recommended, but you could put a bundle of 10 joists down together in one spot and then spread them out. Or at least put them down roughly in position as you're going along and then shuffle them, but you don't have to shuffle them and get the height right. So they're a lot easier that way. They also help with progressive collapse because it's sat on the top and it's going across the joints of the panels. Panels are of a finite length. So when we have 2 panels coming together, we've got to think about fastening it together for progressive collapse to stop the whole building. If this wall vanishes, will the floor come down? As we talked about the exhibition stands, it doesn't happen like gauge steel, they tend to stay up. This is partly why. We've got fixings that go through the top, or if there's another wall on top, through the bottom track, Z, and into that one, but they bypass that panel joint, so they tie it together along the length. As well as the top of the track and the bottom track if there is one, you've also got the Z, so you've got 3 layers of steel stopping it snapping, stopping it coming apart. They're just a nice, easy way of putting it together. Lots of people can't roll it because it's a Z and you want different lengths, different depths for various reasons. So you might get some resistance from some manufacturers. However, there's not literally every street corner, but the fabricators with a press brake, which is a machine to bend the metal, or even a hand bender. Have you watched any of the car SOS shows or anything like that, you'll see a hand bender. They're about 1 metre long generally. They're readily makeable, and it's 2 bends. They're very simple to make, so they're relatively cost effective. So that's something to think about. We've also got this platform and balloon construction. My personal preference for what it's worth is the balloon construction, sort of illustrated on the right, as opposed to platform. Can anybody think why I might prefer one over the other? There is an engineering reason, it's not just I think it's prettier or anything stupid. Anyone have a guess? There's no wrong answers.
Eccentricity of connection.
The eccentricity of the connection in balloon would be greater this way, but I still prefer it. I prefer it because if we do platform, have the joist on top, and the walls on top, you've got joist, wall, and it's trying to squash it, trying to crush the joist. If it's a lattice truss, like this could be, if that was top, that was level, then either you've got this C-section at the end and it's not quite so bad, but it's there and it's not quite. But if it's a solid C-section, there's a really good chance of you crushing it. Quite literally. It's happened to me in the past. When I was younger, unaware of it, I am now. Got called to site because I crushed the joists. Not me personally. But they put it down, loaded it up, and it crushed the joists. They are ridiculous. It's 1.2 mil thick. You know, there. There's no strength to it, is there? The simple solutions, we just put another piece of C-section wall stud up against the C, up against the joist that goes in and out. We just put a bolt onto it. But it's another operation, it's a bit more faff, etc. But you don't get the eccentricity of load. You also have the question, both ways really, where does the floorboard stop, or the floor finish? If we're doing it as platform, is the floor between the walls? So if it's timber, is it going to get crushed over time itself? Is it going to degrade over time and get any movement and any cracking in the walls? If it's a screeded floor and we're using the decking, is the decking going to crush under the load? Where does the screeding stop? If we're doing a screeded floor and we use Z-hangers, we've got this top track or the bottom track. We can use that literally as like stopping the screed. The screed can't go through if that was the C-section, it can't go through the flange. Unless we're putting holes in it for services or anything stupid. So we can use that as something to screed against. If we're doing it in platform, there's nothing at the end. We've then got to think about stopping the screed. It's not the end of the world. But again, with the screed, 2 or 3 days before we can put the next floor on. So we're getting even slower. So this is why we try and stay away from the screeding if we can, because it can be so many issues. I don't know how to turn the sound up on this, so I have to put with my voice for a second. This is a 4-minute video showing we've designed a 2-storey house. We've combined various calculations together and it runs through it and spits out the answers at the end.
Welcome to our proof of concept for a one-form house. If the interest is sufficient, we will further develop so we can alter the roof span, or different options for roof span, different options for floors, etc. It also only uses C-sections rather than lattices. Again, limitation of the proof of concept. We'll clear, delete all variables, calculate all, wait while Ted thinks about it. Okay. Proof of concept, Eurocodes only. Change the dimensions, length and width, building height, story heights, joist spacing, stud spacing, change the loads, change the window dimensions, have a sketch showing the window, and we have stair openings. Today we're using a 150 by 2 for the roof, the The floor will be a Hadley 305. On the wall studs will be 100 by 2, and we'll add a knocking. Now, proof of concept, we haven't added the pass-fail ratios, etc. They are scrolling past, so that everything has passed. So if I'm going too fast, calculations finished. Using the navigation pane, we can scroll all the way down to the bottom to the summary. Done racking, overturning. Summary restates the sketch with the imagery provided by colleagues at iPro Blue Technologies. Restates the dimensions. The weight of the building. One of the recent changes has been that we can now calculate, and it states automatically the weight per square metre of the floor joists and the weight per linear metre of the walls. We've also, for the purposes of this demonstration, included a calculation for the weight of the K-bracing. Summary of the floor joists, joist centres, etc. And finally, if we switch to Excel, open the one form house XLS sheet in the TEDS directory, it's added the dimensions, the lengths, profiles, number of floors, chipboard type. From here we could then put this into Excel and then link to any other 3D packages. Equally, the 3D package can dump values into here that we could preload into the form for TEDS. So we can have two-way design, engineering and CAD, both can feed into each other. Thank you for your time. If it's of interest, we'd love to hear from you.
Okay, we've since that video produced one for module design, working with Trimble, our friends and partners over there. So we can engineer a module of whatever size we require and get the full weight out. They in turn have developed a pro forma 3D model in their software so that they can detail or do detail the module, so you can then do the full rotation, sections through, etc. Bill of materials, everything from that one form. Literally in Excel, you push a button to export the data, they push a button to import the data. On their side, or the detailer pushes the button, it populates the model, and within 4 minutes you've engineered and drawn, and from there you can manufacture. I haven't got examples here, but on the website there are examples where, working with the Advanced Manufacturing Research Centre at Sheffield, they took a robot and some dry lining studs from Wix, because they couldn't find a manufacturer to respond quickly enough, but they assemble a wall panel using the robot. It rivets it together on this little table, turns it over, rivets the other side. Using the technology that we have here now, just demonstrated in that short video, we could engineer the house, we can detail, draw, model, and produce the manufacturing data for the house. So effectively we then print the house in metal and the robot will assemble it, the panels. It's not science fiction, it's not this is a nice idea, it's here and now. You keep seeing videos of extruded concrete houses and things like that, and robots laying bricks. And this is all a few years old. So it does work. It's just, as ever, it's construction, and like I said at the start, the Romans and children recognise what we're doing, so we'll get there eventually, won't we? Anyway, back to maths and today's discussion. Wind, this is a screen graph from Package called Breathe, which was written in the 80s.
So you have by 17 minutes, right?
It tells us we tell it the location, 6-degree grid reference. It tells you basic wind speed, pressure, etc., wind speed for that area. And from that we can then generate the overall load for this racking and whether the studs are going to deflect, etc. Horizontal members, roofs or floors, ceilings, lattices, etc. Stud members we've looked at. Progressive collapse. It only applies to certain classes of buildings in the UK. I think we classify it as 2A, B and 3. 2A is regular domestic stuff. Don't worry about it. Anything of 3 stories, like 2 stories and space in the loft. 2B is anything over that. You just need to run a very, very quick basic check of are these members, the Zs, if a vehicle crashed into the side, if one wall was removed, would it collapse a certain length of that wall? It's relatively simple, but the phraseology and the codes and trying to find a word to example is difficult. So working with others, we've developed something to help people do that. Facades, opening in walls, lintels, etc. The racking, I keep talking about. K or sheathing. Others in the industry will talk about cross-flat X-bracing. I'm vehemently against it because when you put a piece of flat metal in the wall, no matter how you try, there's going to be a slight bow to it. I'm exaggerating it here. Then as we parallelogram the wall and the bracing then stretches out, that 2 millimetres or so of deflection in this way to straighten out is 2 or 3 millimetres of extension, and that's more than we're allowed. We then start getting into second order effects, which in plain English is if it's flat, straight, the stud, it's fine. If it gets to that point and we're pushing down, it's then going to start having a second order effect. It's going to start making it worse. So we end up having to reiteratively check it. So it goes that far under that load, right, so we've got to check it again and check it again until as soon as you start getting into second order effect territory, it's over. Just stop. We've got to put more bracing in, and that's all it is. But using cross-flat bracing, apart from one company I've seen them have a kind of a U-section that they screw in and take out that bow, they take up the slack. And even then, if you're bang against the wall, like in a flagpole, you can hear that rattling, no matter what they do, because it's metal against metal. And then I go, we'll just put fixings where the strap crosses a stud, we'll put fixings in. Right. All you're doing is that 2 millimetres over the panel, you're reducing it to fractions of a millimetre over 600 millimetres. It's still the same problem. You've still got that bit of play, and it's still going to stretch. It doesn't go anywhere, you just don't hear the rattle. So it just does not work unless one particular manufacturer. So we use K or sheathing, as we talked about. Fire, I've banged on about it a lot. These two are the most critical bits. The one actual fire test I've witnessed myself rather than seeing the reports and things, it failed at 56 minutes rather than 60. They hadn't put screws at 150 millimetres at the edge of the board. there was nothing to fasten to in one direction or something like that, you know, along the long edge. So they fastened it with the joist, but in between, there's nothing there. So within the first 5 minutes, the first layer of plasterboard failed at that point, started to hang down, the fire got in, affected the inner layer, and within 10 minutes the fire was licking through all the fire protection and blooming floor failed 4 minutes early. So it is critical, and that's sort of made me wake up and listen again. Acoustics, and thank you. My contact details are there. Are these slides available for?
Yes.
Yep, so you've got all my contact details. I can happily leave cards, etc. The samples here, if anyone wants to take anything with them, save me carrying it home tonight.
Thank you very much.
Thank you
very much. Please join me in closing this presentation. I think it was, the most important thing of all of that is that you need now to think when you pick your design. If you go for something like that, although it's brilliant designs, it's limitless, you can do pretty much everything, there are a lot of factors that we need to consider, more than standard designs, and because there is so much in the literature at the moment, a lot of research is actually working on developing design guidelines and knowledge on the topic. I think that's why the presentation was quite helpful, just to see that, the breadth and you need to have in mind. And I think, as I said at the beginning, that it's really rare where you see all that experience in one presentation. It's not just reading the book, it's linking all these factors together when you get a decision. So thank you very much for the presentation. The material is uploaded. I think I also uploaded since last year some worked examples, some extra PDF files, calculations and stuff.
So my contact details are there. If anybody wants any other resources, I'm very happy to share.
Yep. So there are actually there are 2 companies there.
This is a consultancy, engineering consultancy. The other side is the software business.
So maybe you will not use them for a coursework this year, unless you do like a project on modular construction. But since next year you'll be in practice, you definitely have a good contact, someone to ask if you're about to work on modular stuff. Yeah. Any questions? No. Yes.
You said for light gauge steel that it's not particularly suited to big bending moments. How would you then approach a larger span?
Very good question. The larger span, in terms of a floor, is predominantly deflection based, unless we get into particularly high plant room type loads or gymnasium of 5-7 kilonewtons per square metre compared to 1.5. It's a deflection that limits and not the strength. When we're looking at 30-metre portal frames, we design all those as pin jointed frames. So the bending moments are minimal, 0.1, 0.2, if that. It's all in the axial loads, hence we plate the connections, we transfer the forces. It's just thinking about how we apply those forces and not applying a bending moment, finding ways to not do it, because they do fail. And I say, unfortunately for me, I have 2 or 3, maybe 4 times fallen foul. So I know it does happen. It's not just me being an engineer being a bit like, oh, might. No, it has happened, and I have a leg on my face, and yeah. I'll push the boundary as far as we can, and I'll work on the edge of the envelope, etc. And I'll really push it as far as we can. But I am conscious that I have gone too far in the past, and it does go wrong. So I know not to do it again. And hopefully I'll pass that on to you, so you can learn from my mistakes. There have been a few, 3 or 4, but I'm man enough to admit them all. Big enough, I should say, not man enough.
Any more questions?
Is there any scenario, like any cases that you realize this type of lightweight steel just sometimes doesn't work? You have to comply with other regular steel or
Yes.
other materials.
Absolutely. I am a huge proponent of light gauge steel. I think it's absolutely fantastic. Best thing since sliced bread. However, even I happily admit it's not a panacea. It is not perfect for every single thing. Example, portal frames. Under 15 metre span wide, I think light gauge steel is fantastic and can really help and is cheaper. Over that, people have been in hot rolled steel frames for 100 or so years for a reason. They work. There are certain spans, easy to see, where the depth we can do. I did a 12 metre square conference centre in a NATO base. Great, but the floor joists are 1200 millimetres deep. At 300 centres, I think it was. You could almost carpet it. It was ridiculous. You don't need boards, it would go straight over the carpet. It was nearly solid. But where they were, like the Mongolia thing, it was £15,000 to fly a piece of hot rolled steel in. So this worked. Yes, it might have been horrendously expensive to anybody else, but for them it was. But you're sitting there looking at it thinking, this is stupid. There's no other time in the world this would be a sensible idea. And 95% of MMC's customer base are manufacturers of light gauge steel. They're not manufacturers of hot rolled steel. So we will do everything we can to design it in light gauge steel because that's cheaper for them. It's their cost, etc., rather than buying something in and they're not reliant on somebody else. But even then, there are times when you just look at it and say, oh, I'm really sorry, we can do this, but
There's a better solution.
yeah, even I am saying there's a better solution,
Yeah.
so they know it's.
For different applications, you have, of course, the optimum solution is not one. I'd say that this is where we also move for certain applications, and especially lighter buildings when they're exposed to extreme loads, to hybrid systems, right? So you have more than one material as the main structural material that you build. So you have light gauge steel and hot rolled steel, or you may have a concrete core, or some shear walls. So you combine two structural systems. That's why it's called hybrid, to make the best use of the material. Can I make a question?
Of course you can.
Is there anything in particular that you design differently in foundations when you have a modular building, as opposed to a traditional steel frame?
Yes. When it comes to modular buildings particularly, and thinking of the hybrid thing 20 years ago, more, the McDonald's have hot rolled posts in the corners, and then it can be clear, absolutely, apart from the four posts, nothing else. And we could design those with moment stiff connections, even in the side beam, so that gets the rock in that way. Well, that's sort of beside. What ties into, because of that, this fairly deep side beam, 300-400 millimetres deep, is not uncommon, and that's fine. But then you start thinking about the architecture and trying to get in buggies, wheelchairs, etc. It's like a jump, isn't it? But that side beam can readily be designed to span 10 metres between supports. So if you're in boggy ground, peaty, there is no ground bearing pressure, we're putting ridiculously deep strip foundations and things in, we could put screw piles or pile foundations of any type, and the module will span from support to support, a little like the very old brainstorm we saw. They will span from pier to pier. So in that case, yes, we would design specific foundation, or we would think about the foundations from that viewpoint. There are many reasons, not just poor ground conditions. Concrete's quite expensive, it's labour intensive, putting a couple of piles in, or even pads. There's a company called Jackpad who, I think it's recycled tyres, but they're basically look like glorified paving slabs, but they're about that thick. And they just use those. One of the issues is the racking and how we calculate it, and this is why I started researching it. There are issues with that overturning and what the reactions are, but yes, we start falling into the adage of you get 2 engineers in a room, you get 3 answers. Professor and I get on really well, but if you commission us to do some work, we still might give you 3 answers. The one that we both agree on, and then our own takes on it. So there's no right or wrong.
Yeah, absolutely.